Hello, everyone. Welcome to the seminar on digital quantum magnetism at the frontiers of classical simulations. My name is Dr. Tanya Rusi. I'll be hosting and moderating this. So it is my pleasure to introduce Dr. Michael Foss Feig. He's been with Quantinuum for 7 years now. Before that, he studied under some real giants in AMO physics. He did his PhD with Dr. Anna Maria Ray at GILA, and then his postdoc with Dr. Charles Clark at NIST. Mike, take it away.
Thank you, Tanya. Thanks for the introduction. Like Tanya said, my name is Mike Foss Feig, and I'm just going to jump right in. I just want to very quickly, before getting into the material, highlight that I'm excited to represent just a small part of what's going on in this much larger company across the entire world. So I am located myself in Denver right now, outside of Broomfield, where some reasonably large fraction of the hardware effort is located. So the quantum computers that I'll be talking about in this talk are located here in Broomfield, Colorado. So like basically any talk on quantum simulation, I'm going to start off with an allusion to the origins of the ideas of quantum simulation, or simulating quantum systems with quantum computers, which many people attribute to Richard Feynman, but certainly to a variety of people in the early 1980s. And they had the insight that quantum mechanics, at least if you're talking about the quantum mechanics of sufficiently complex systems with many particles, is not something that can be easily simulated with a classical computer. But it was plausible even at that time to people that if you had a computer built out of quantum parts, a quantum computer, you should be able to efficiently simulate many quantum systems. And it took a relatively long time after that idea first emerged for this to actually be formalized in any way. And so as far as I know, I think Seth Lloyd was the first person in the mid-90s who understood how a real universal digital or gate-based quantum computer that can just apply operations to small groups of qubits at a time could simulate essentially any local or realistic kind of physically reasonable local quantum system. And once that was realized, relatively quickly, people extended this to all kinds of other systems, including, right away to Fermionic systems, and then, over the next 15 years, even to systems with infinite quantum degrees of freedom, like quantum field theories. And so the point I'm trying to make is just that there's been this evolution from the very early days of this idea to today, where people have progressively realized that these kinds of computers are flexible enough and powerful enough to simulate a huge variety of systems we encounter in the natural world that are built out of quantum parts. But unfortunately, even though these ideas are 40 years old, I would argue, this dream or this vision for quantum computers as quantum simulators has largely not been realized to date. And that's not to say that people haven't done impressive things. In particular, I want to call attention to the whole field of analog quantum simulation, which is a little different. So these are, for the most part, atomic systems that are, tailor-made and are designed to, in an analog fashion, simulate a particular simple model. And I would argue that these kind of systems, including neutral atoms and some trapped ion systems or arrays of Rydberg atoms, have done things that are arguably classically hard to simulate, but they've done it in a way where the machine was built, tailor-built for the particular problem they were trying to solve. And the hope with, universal digital machines is that we'll have the flexibility for a single machine to tackle a very wide array of problems and to simulate a very wide variety of physical quantum systems. Unfortunately, there's a lot of challenges with actually getting digital machines to the point where they can simulate sufficiently complex systems that classical simulations are out of reach. So using them as tools where there is no alternative, there are no viable classical methods, is something that people have envisioned for a long time, but I would say not yet achieved. And so it's worth taking a minute to think about why that is the case, why it's been so difficult to achieve quantum advantage with digital quantum computers. And the reason is relatively straightforward to understand. It's basically that if you have a quantum computer that can apply gates to qubits, so here's an example of just 6 qubits in this case with some 2-qubit gates occurring between them, with time running up. In this kind of a setting, if you want to do something that a classical computer can't do, it's crucial that you build a state that has enough entanglement that it can't be represented efficiently on a classical computer, because otherwise the classical computer can just simulate your quantum algorithm and you can't be doing anything that's not possible classically. And so to get enough entanglement, you have to apply a lot of gates. And the problem is in current quantum computers, in the absence of very large scale computers with error correction, these gates inevitably come with noise. And very sort of simply, you can just think of noise as a competing effect, whereas the gates ideally are building entanglement. When noise happens, or when a gate is corrupted by noise, the qubits that it acts on tend to be unentangled from the system. And so as you're trying to build up this entanglement, you're fighting this noise that's disentangling qubits. And as a result of that, limitation on the entanglement, you build classical methods such as those based on tensor network methods, represented here over on the right, are going to have an easier time simulating the system by exploiting the limited entanglement that's created. So that is really the fundamental challenge. I would say it's one that to a large extent can be overcome, and people have already seen this over the last 5 or 6 years. And the most well-known example of people using digital quantum computers to do things that are arguably very classically hard is something called random circuit sampling. And I won't get into any details about what this is. It's not even really important for this talk. Although the structure of the problem and why it was chosen is kind of important by way of example. And so you can think of random circuit sampling as basically a game that we play with quantum computers to try to run circuits in which every gate pulls its weight to the largest extent possible, by which I mean it imparts the largest amount of entanglement possible. And so in superconducting qubit architectures that are primarily laid out in 2D grids, going all the way back to the original demonstration of random circuit sampling by Google, the game that was played is you have some fixed geometry in which you can apply gates between qubits, but you can optimize the type of gates and also the order in which they're applied to try to spread entanglement in the system as quickly as possible before noise sets in and destroys things. And more recently, demonstrations with trapped ions, we've been able to use the flexible connectivity between qubits we have in our architecture, which I'll talk about later in the talk, to optimize not just the types of gates we apply, but also the geometry in which we apply them. And by doing this kind of optimization, we can actually achieve very highly complex states that can't be simulated classically in such low depths and with so few gates that we can do it almost without any noise in the system at all. And so being able to do that begs an important question, which is if we can now do this well, at least for these kind of win at all cost strategies where you even win at the cost of maybe the algorithm you're running is something you don't particularly care about or get any utility out of. That's not. There are things you can do with random circuit sampling, but it's like fairly narrow in scope. But what you'd really like to do is use quantum computers to simulate, to perform useful algorithms. So one great example that I started the talk with is to simulate quantum systems. And if you want to achieve quantum advantage, not just on random circuit sampling, but on some more structured algorithm, the reason that that's been challenging and remains challenging today is that if you take a quantum algorithm for solving some structured problem, inevitably what you find is that there will be a limited amount of entanglement that is imparted per gate in the simulation. And so if you think of a few different example algorithms, so here in this plot, I'm going to show the number of quantum gates you need on the x-axis to achieve a given classical cost or amount of entanglement on the y-axis. Random circuit sampling is an algorithm that was designed to have the steepest curve possible, right? So that what happens is you get to some, fuzzy limit that will say, separates classically feasible from classically infeasible to simulate circuits. You get there with the smallest number of quantum gates and therefore with the smallest amount of noise. And for other more structured algorithms like quantum simulation or factoring, passing that threshold is going to require many more gates and is therefore more technically demanding from the standpoint of how good those gates need to be. The primary achievement of this work that I want to talk about is we've made now a lot of progress in pushing from random circuit sampling into the realm of quantum simulation, where by achieving higher gate fidelities in these new machines, we're now able to do some useful, very structured algorithms in a way that I would argue is beyond the limits of what classical computers can simulate, or at the very least would require truly heroic classical efforts. Okay, so the specific problem that we chose to try to find something where we could achieve useful quantum advantage was specifically looking at the dynamics of magnetic systems, so quantum magnets. And the reason for that is relatively straightforward. So if you take a quantum magnet and you zoom in on what it is microscopically, it's just a bunch of a couple of microscopic quantum spins. So the sort of elemental unit of magnetism in quantum mechanics is the spin, and the spin maps perfectly with no real overhead onto a qubit. So it's very easy to take a quantum magnet and to write down the description of its Hamiltonian as something that acts on a bunch of qubits in a quantum computer. There's almost no overhead for doing that encoding. And so the challenge that's left behind that we've kind of distilled out is the remaining fundamental challenge of doing quantum simulation with digital quantum computers. And that challenge is that in real systems, in quantum magnets, for example, time evolution happens continuously, right? So, if you have a system that evolves in time according to some Hamiltonian, that Hamiltonian is just always on, and it's some monolithic thing describing interactions that are simultaneously happening between, many possible pairs of qubits, for example. And on a quantum computer, we can't really do that. On a gate-based quantum computer, we have the ability to apply interactions between small groups of qubits. For us, it would just be, single qubits or pairs of qubits at the same time. And so you have to find some way of approximating this monolithic time evolution object with a bunch of discrete gates, the way that's shown over here. And so there are many ways to do this, but one common way that we'll employ in this work is something called trotterization, and I'll talk about it later, but that's really what's being shown. And so, one price you pay when you decompose this object on the left into a bunch of gates is that to do a good job of it, so to make this decomposition accurate, it's important that every gate here corresponds to a very small amount of physical time evolution on these qubits. And it kind of makes sense that if you want to digitize something continuously, or if you want to approximate an integral with the sum, you should take, very small bins. It's the exact same thing here. But the problem with that is that now every gate imparts a very small amount of entanglement. So we're running away from this limit that random circuit sampling lives in, where we're optimizing the dynamics to ensure that entanglement builds up as fast as possible relative to noise. And that really is the fundamental reason why it's been challenging to date to use digital quantum computers to do quantum simulation at a scale where classical simulations aren't possible. So I want to delve into a little more detail about why doing effective discretization is really critical. And it's not just a question of quantitative accuracy. There's more to it than that. And the story can be understood as follows. So in a real physical system, any real physical system really, time evolution happens in continuous time. So here's the Schrödinger equation describing any quantum system evolving in time under its Hamiltonian. And this equation is invariant under continuous translations of time. And so, we know from Noether's theorem that symmetries or invariants under translations such as in time are in general going to correspond to associated conservation laws. And in particular, translational symmetry under time leads to the conservation of energy. It's what's responsible for energy being conserved in real systems. And, energy conservation is something that's fairly familiar, I think, to everybody, but it has relatively non-trivial consequences if you start thinking about how complex systems evolve in time. And the reason can be understood by a very simple classical analogy. And it really is sort of a very cartoon, but somewhat accurate picture of what statistical mechanics tells us about complex systems. And so imagine you have a glass of water and you drop, a little bit of dye into it, as is shown in this picture. The premise of statistical mechanics is that if the time evolution is sufficiently complicated, as it is here, then at late times, it doesn't really matter that you can't track the details of what's going on exactly. If you look at any particular location at much later times than this snapshot was taken, what you'll find is that they all look the same, and the color of the water is only determined by the amount of dye that you put in at early times. Right. And so the general statement that I'm trying to make is that at late times in complicated systems, classical or quantum, all of the relevant features that you would look for to characterize that system or that material are going to be determined by the conservation laws you have in the system. And in particular, energy, the conservation of energy, will lead to an effective temperature at the end of the day that these systems exist at, and that describes the behavior of all local observables. Now, that example was entirely classical, but it applies equally well in some sense to quantum systems, although the story is a little bit more complicated, especially if you think about not a quantum system that's in contact with a thermal bath, but an isolated quantum system, which to a good approximation, a quantum computer is. But even there, there's a pretty well-developed understanding now of how the thermal behavior and equilibration and statistical mechanics emerges in late time dynamics of complex systems. And it's also understood, therefore, how conservation laws impact what we see at late times in the dynamics of isolated quantum systems. And it's somewhat of a complicated story, and there's many things that are still today not fully understood, but there is broad consensus about the contours of this story. So I'll give like a 1-minute sketch of how it goes. And that is, imagine you have some sufficiently complicated quantum system that's just, sketched here as this gray area. If it may be true that this entire system is isolated and therefore has no entropy, no notion of a temperature. But if you zoom in and you look at some small subsystem, it's not so unreasonable to think that for a small subsystem, the rest of the quantum system itself might serve as an effective bath to thermalize that small subsystem. And indeed, it's seen that is what happens. And it's been observed in many experiments and also in numerics that at late times, if you look at local observables in a sufficiently complicated quantum system, they will converge to thermal expectation values. They will converge to having an expectation value that is governed by a thermal ensemble, where the temperature of that thermal ensemble is set by the associated conserved quantity, meaning just the energy density of the initial state. And that's all a little funny because there's no real true entropy in this system. It's just totally isolated, and it's in a fixed state. But the notion that a small system thermalizes is intricately related to the existence of entanglement in the quantum dynamics. And one very important consequence of entanglement is that the fact that this small system becomes entangled with the rest of the system, that entanglement and the entropy associated with it, the fact that it causes this small system to not itself be in a well-defined state, really is what plays the role of temperature in the thermalization of a small subset of an isolated quantum system. So I make this point because we'll come back to it later in the talk. It's important to remember that entanglement and temperature are very closely connected in thinking about the thermalization, the effective thermalization of a time-evolving isolated quantum system. Okay, so all of what I just said applied to just continuous time evolution of the physical world around us. The story is a little bit different in a quantum computer because of something I already mentioned, the fact that we have to approximate continuous time evolution with a set of discrete gates. And so let's drill down a little deeper on this example of trotterization. So I'm not going to say exactly what this means, but very loosely, if you think about time evolution under a Hamiltonian, in many cases you can break it down into a sum of terms that act on, say, in one dimension in this simple example, terms like the dark gray gates here that act on even pairs of qubits, and terms like the light gray gates that act on odd pairs of qubits. And so you can just alternately apply these different even and odd terms, or A and B. And if you do that, and if you make the time step with which you apply A and B small enough, eventually this dynamics, as the time step goes to 0, will begin to approximate the true time evolution in continuous time of the system. So this is this is basically what Seth Lloyd, realized back in 1996 when he figured out how to bound the error of a digital quantum computer simulating a physical system evolving in continuous time. And so, the one problem with this picture is that, I already said that the conservation of energy is related to time translation symmetry. And if you look at this circuit at any finite time step, it's not really invariant under continuous time translations. It's invariant under discrete time translations of order the time step being used in the trotterization. And so very generically, when that happens, when you have a system without time translation invariance, you expect it, absent any other conservation laws, if it loses conservation of energy, there's no reason for it to evolve at late times into anything other than essentially a completely random state. And so in a circuit like this, if you propagate it for long enough, or evolve long enough in time, you always expect the state that comes out to be completely chaotic or random and really have no interesting local structure. And this is very much the situation in something like a random circuit sampling experiment. And what must happen is the time step becomes small and energy is approximately conserved. As you move from this large time step chaotic regime where observables just kind of all go to zero immediately, eventually, per the discussion on the previous slide, what should happen is that they will converge to thermal values as energy is approximately conserved. And over the last maybe depends on exactly what you mean, but let's say 5 to 10 years, I would say a much more detailed understanding of what happens as you transition from large time step to small time step has emerged. And the key word here is prethermalization, or flow-K prethermalization. And what people realized is that as you turn the time step down, very quickly, you develop thermal physics with respect to not exactly the Hamiltonian that you're trying to simulate, this H, but a dressed Hamiltonian that looks a lot like it for small time steps. And that prethermal behavior, while it can't live forever because the late time limit will always be chaotic, it can live for a time that's exponentially large in 1 over the time step. And exponentially large really means that you don't actually have to make the time step all that small before you just don't care about the fact that prethermalization doesn't live forever. It is essentially going to, a system with a reasonably small time step should essentially, for all times you care about, give you thermal-like behavior and therefore look very much like a natural physical system that you might want to simulate. Okay, so with that setup, I want to now dive into a little bit of the details of our quantum computers before then moving into a discussion of how we actually simulated some of the physics I was just discussing and push the time step of our simulations down to the point where we can really observe the emergence of conservation of energy and the real dynamics of a very reasonably realistic magnetic system. And so our quantum computers, you can see in this beautiful picture, they are based on surface electrode traps. So this is a substrate upon which gold electrodes are printed. Every little rectangle that you see here is an independent electrode. And they're all wired up under the surface so that we can apply independent voltages to these different electrodes. And in that way, we can sculpt a potential energy surface for charged particles over the surface of this trap, and we can store ionized atoms in it. And so in this particular computer, those ionized atoms are ytterbium-171 ions. And right now, we store 56 of them above the surface of this trap along this kind of ring-shaped area that's shown here. And I don't want to get into too many details about how the computer works. It's not that crucial for this talk, but I will just say a couple of key things about how our quantum computers work in general, the operating principles. So the first is that the actual qubit, every qubit, is encoded in nuclear spin sublevels of the electronic ground state of a ytterbium ion. And in particular, we use what are called hyperfine clock states. And the only thing important to know about that is that they have a very stable energy difference. And that means that they have a very long coherence time. If you put a qubit in a superposition of 0 and 1, it will stay in that superposition with the phase you intend for a very long time. So that makes them good qubits. Another detail that I like to mention, just because it's worth keeping in mind, in some ways, how much is going on under the hood to make this happen. I'm showing 56 ions, but in reality, we also have to keep those ions cold during a circuit in order to make the gates function correctly and well. And we do that by co-trapping them, in this case with barium ions that we can then laser cool. And by using a different species barium, we can laser cool the barium without impacting the quantum information stored in the ytterbium. And the barium then acts as kind of a thermal bath that pulls energy out of the ytterbium and keeps it cold during the quantum circuit. And then the final thing is all of our operations, all quantum operations, so that includes state preparation, measurement of the qubits, applying 2-qubit or single qubit gates. All of these things are done by addressing with lasers that skim over the surface of this trap. So the one thing that is not so obvious if you just look at this system is what gates it's actually possible to apply. If you look and just think about it superficially, it seems like these qubits live on a line. And so you really should only be able to apply gates between qubits that live next to each other by bringing them into these locations where I'm showing them paired up that we call gate zones. So these are the locations where lasers cross over and in which we can do gates. And that connectivity would be rather limiting if that's all we had, but in fact, we have much more than that. And the reason is, imagine, I'll show you through an animation. Imagine you have all your qubits lined up in this ring and I've color-coded them. And maybe you've just done a gate between the purple and the pink one, but the circuit that was given to you, which is shown schematically by these lines connecting qubits, might be a pattern of 2-qubit gates that's asked of you in a circuit, asked of the computer in a quantum circuit. And if now these gates are not arranged in 1D, but they're laid out in some arbitrary pattern, we'll find after gating these two ions that the very next thing we need to do is we need to gate ions that are living far away from each other. And that we're able to do because we can actually pull these ions apart, and we can also move them past each other by rotating these crystals. And this was just a very simple operation shown with 4 qubits, but we can build out of this primitive operations a complicated transport protocol by which we arbitrarily rearrange all of the ions so that all of these long-range gates now are acting on qubits that have been brought next to each other, and they can then be cycled through the gate zones and gated together efficiently. So we often say that these computers have all-to-all connectivity. This is what we mean when we say that, and that's going to be relevant because in the end, we're not going to be studying a one-dimensional model. We're going to be studying a model with a more interesting geometry. Okay, so with all of that lead up, I want to get into the details now of what we actually did for simulating quantum dynamics. And so I said we were going to be simulating the dynamics of a magnetic material. What I really mean is that we're going to simulate the dynamics of a relatively simple, admittedly, model of quantum magnetism. So it's something called the transverse field Ising model. And I've written it out here. If you're not familiar with it, it's a relatively straightforward model. So this first term here is a sum over all pairwise products of Z operators on the qubits. And what that really means is just because of the negative sign out here, this Hamiltonian, or energy, will be minimized when the value of Z is the same on neighboring pairs. So when neighboring pairs of qubits are either both in 0 or both in 1. And so this is a term that prefers ferromagnetism. This other term makes things more interesting. In the absence of this term, the ground states would be just classical states of all qubits in 0 or all qubits in 1. This term does not allow those states to be eigenstates because it causes bit flips between 0 and 1. And you can think of it as introducing quantum fluctuations that destabilize this ferromagnetic order preferred by the first term. And so, what we chose, since we have 56 qubits in H2, we chose to arrange this model on a square lattice that was 7 by 8. 7 by 8 just multiplies nicely into 56. There were actually other technical reasons why we chose a square lattice, but it's not so important right now. And we also, had a choice to make about the boundary conditions for this lattice, and we chose to put it on a torus for a relatively natural reason. It's just that by putting a system on a torus or by imposing periodic boundary conditions, this is a very common trick played even in classical numerical methods to minimize the effects of the system size being finite and to be able to read off of a relatively small finite size system more accurately what should happen in the limit of a very large system. So this is a natural thing to want to do. It would be very difficult to do in a system built out of qubits with fixed locations. It'd be very hard to imagine actually printing qubits in some kind of a material arranged on a torus. H2 doesn't really care what lattice we choose or what boundary conditions we impose. It's kind of all the same for running on this computer. And the reason we chose this particular model, there are a couple of reasons, but I would say the main one is that despite the fact that it's simple, it is complicated enough to show a lot of very generic physics and also to not have any exact solution. So it's a good test bed for whether you can do anything that can't be done classically, since there is no efficient classical way known to simulate this model in full generality. And so the thermal physics of this model is pretty well understood, and it's kind of mapped out in the phase diagram over here. So what I'm showing is on the x-axis, the strength of this transverse field term that's trying to destabilize the ferromagnetic order through quantum fluctuations. And then on the y-axis, I'm plotting temperature, which is again trying to destabilize the ferromagnetic order through thermal fluctuations. So you can think of these axes as quantum and thermal fluctuations. When both of them are small, what you find is that you get true long-range ferromagnetic order in this model. So that means that if a given spin is up, you're very likely to find, even arbitrarily far away, that another spin is pointing in the same direction. So they'd either both be up or both be down. And then there's a line of finite temperature phase transitions where when fluctuations become too large, that order is lost. And the system is referred to as paramagnetic, meaning that it does not spontaneously order in either the up or the down direction. And then at zero temperature, even though there's no thermal fluctuations left, quantum fluctuations induced by the transverse field can also destroy that order. And so there's something known as a quantum phase transition sitting down here at zero temperature. And this is a very, generic style of phase diagram that you'd expect for a finite temperature quantum model. So, our goal at the end of the day is going to be to show that this kind of thermal physics, which you would expect to emerge out of dynamics if you had a continuous time system, a real, like realistic system, but you might not expect to emerge in a digital quantum computer if the time step is too large, since energy conservation is lost. We want to show that we can actually take the time step small enough and have gates that are good enough while doing that, that we can observe thermal physics that comes out of the time evolution approximated by a trotterization. And so, I briefly described trotterization before. I won't say a whole lot more about it right now, except for experts, I'll just say what we use as a second order product formula. And the important thing to know is if you zoom in on just a small subset of this circuit, so just a handful of qubits, I'm showing what happens as time goes from left to right here. What you're doing is you're just alternately applying 2 qubit gates first along the even bonds in the y direction, then the odd bonds, and then same even and odd bonds in the x direction for 4 layers of 2 qubit gates per little time step dt. And this little time step being small just means that each of these gates, what I'm calling a UZZ gate, it's some entangling gate that imparts just a parametrically small in dt amount of entanglement for the system. So let me just describe now how you would expect that thermal physics to emerge from dynamics, or I should really say pre-thermal physics, since the time step's not zero. And remember, so the idea is if the time step is small enough, then the dynamics should reveal the thermal phase diagram with a temperature set by the energy density of the initial state. So all local observables at late time should reflect thermal physics at the temperature set by the initial energy density. And so we don't have any access to temperature. There is no true notion of temperature in this isolated system, but we do have access to the initial state energy in a very simple way. Even if we start with a trivial state where every qubit is independent of every other qubit, we can tune the angle of every qubit on the Bloch sphere, so this angle theta, to tunably control the energy of the initial state with respect to the Hamiltonian. So this is a very trivial form of state preparation that gives us a knob to turn to control the effective temperature that the dynamics should saturate to. And now what you expect is really for any local observable, based on the arguments I was giving earlier, it will undergo some dynamics that will eventually settle out and equilibrate to a value set by the expected thermal value at the temperature associated with this initial state energy. And so what we're hoping to be able to do is take the time step small enough that this pre-thermal regime is long-lived and we can actually access true equilibrium physics in this pre-thermal regime. And here's an example of what you'd expect to see. This is just a numerical simulation on a small, I think it was 4x4 system. And I'm showing a phase diagram of sorts where I'm scanning on the x-axis, again, h over j. The previous schematic phase diagram I showed you was t on the y-axis. Now I'm letting theta be a proxy for t. So I'm scanning this angle to control the energy density and therefore the effective temperature things thermalized to. And if you plot, in this case, we're plotting the Ising order parameter, not exactly expectation value of z, which would be the Ising order parameter, but the expectation value of that squared. And there's a reason for that, but it's not so important. What you see is that at long times, if you plot what values it takes on large values in the expected ferromagnetic regime and then small values outside of it. So at least in this very small size simulation, we can see that thermal physics or equilibrium physics is observable in the dynamics of the system, despite having a finite Trotter step. And for this simulation, I think the Trotter step size was 0.25. And let's zoom in on what happens as you change that Trotter step. So here's that same observable. Again, the square of the Ising order parameter. So this is characterizing whether you have ferromagnetism or not. We're plotting it as a function of Trotter steps, so that's really just playing the role of time up to a factor of the time step. And indeed, for small Trotter steps, you see that while there are finite size effects, and increasing the system size from 3 by 3 to 5 by 5 impacts the value of this order parameter, we see that the existence of a stable prethermal plateau is relatively robust to increasing the system size. Although if you increase the time step by not all that much, so say to 0.3, what you find is that while small systems remain stable and show thermal behavior, you increase the system size and immediately things just kind of collapse to completely chaotic states or infinite temperature. And so it's reasonable to ask at this small time step, even though numerical simulations on small systems where we can do them show that the system is stable and exhibits equilibrium behavior, what will actually happen as we grow the system size to the 7 by 8 system that H2 can currently handle? Will it pre-thermalize, or is the time step too large and will it completely collapse? And I think this is an interesting question to go and investigate, in part because there is, to my knowledge, no known efficient classical way to answer this question, because you basically just have to go and accurately simulate the dynamics of this complex quantum circuit. Okay, so we thought long and hard when we were doing this about where this question would be most difficult to answer on a classical computer, and therefore where a quantum computer would help the most. And the picture we kind of settled on is based on this connection between temperature and entanglement that I mentioned earlier. So, I'm putting here 3 different points in the phase diagram that are at different effective temperatures. And what I'm showing on the left is for those different points at late times, how much entanglement there is in the system. And this is just measured in entanglement entropy in some normalized units. It's not super important. The important thing is the qualitative trend that at late times, so as we evolve along the time axis here, at low effective temperatures, you have low entanglement, truly because entanglement entropy is playing the role of thermal entropy, whereas at high temperatures, you have large amounts of entanglement. And so right away, it kind of tells us that low temperature is not a great place to be sitting at right now for achieving quantum advantage, because the corresponding low entanglement entropy suggests that classical methods that exploit low entanglement might be too effective and might make these simulations possible. On the other hand, if you go to too high temperatures, there's a separate problem, which is that at high temperatures, the system has relatively weak correlations, and you might then expect accurate simulations to be possible just by kind of breaking up the system into small chunks within which those correlations are relevant. So again, despite the large entanglement, there might be other classical methods to simulate the problem here. And we think, right now, this kind of Goldilocks region where quantum computers can really help and get beyond the limitations of many classical methods is at this regime of intermediate entanglement entropy or intermediate temperature. And so we chose a point that was kind of close to the finite temperature phase boundary, ferromagnetic phase boundary. And we did that, again, so that it would have reasonably large amount of entanglement, but by virtue of not being at high temperature and being close to this phase boundary, there would be a lot of long-range correlations that truly require you to simulate the entire system in its totality to capture accurately. Okay, so with all of that as a prelude, I'm just going to show you some quantum data now. I mentioned in the previous slide that this quench at low temperature is expected to be possible to simulate classically due to its low entanglement. For that reason, we didn't focus on it, but we did actually run this quench to use as a benchmark of the quantum computer, since we could do classical simulations there. So we first took this initial state angle to correspond to this low temperature, and we took data on H2. And the data looks like this. So I'll explain what's going on in this plot relatively slowly. So on the x-axis, again, is the Trotter step. And once again, we're plotting the Ising order parameter. So we're determining at late times whether the system saturates to a state with a finite order parameter or not. And the raw data out of the quantum computer with no processing at all is shown in blue. And we used a variety of error mitigation techniques to try to improve the quality of that data. It looks reasonably accurate, although clearly it's not exactly agreeing with what I'll describe to be what we believe the classically computed ground truth for what should happen, this purple line. And so we applied a couple of different techniques, but probably the most important one here was something that's relatively well studied and was developed maybe 6 years ago or something by researchers at IBM called zero noise extrapolation, where we inject more noise intentionally into the system to get this greedy data. And then we use these, the values of the observables at two different levels of noise to try to extrapolate out what it should have been in the absence of any noise. And, that procedure is reasonably heuristic, and that's why we really wanted to have a benchmark quench with a ground truth computed classically to validate whether that procedure produces accurate answers. And so that classical ground truth we obtained, or really our collaborators at Fermioniq obtained by doing something called matrix product state simulations. It's not really that important what those are, but they're, a method of simulation that works very well at low values of entanglement. And, if you know something about this, the bond dimensions that they achieved were actually relatively large, and then they had to extrapolate to the limit of infinite bond dimension to get a classical answer that was accurate. These are not actually easy simulations, but they are manageable on state-of-the-art GPUs. And so we believe this purple line is accurate, and then we believe that these error mitigation techniques we're employing can bring the quantum data in agreement with the correct answer for this quench. So after building some confidence in that, we went on to study this intermediate, more correlated regime where I wanted to show you one more thing just because it's kind of cool. Before I move on and say what I was going to say, if you look even at the very latest times, so out here at 20 Trotter steps, for context, these are circuits that involve between 2,000 and 3,000 gates. So they're extremely deep circuits with a lot of gates. Even in the raw data without any processing, if you zoom in and look at a bunch of different shots, so every little square here is a different sample from the quantum computer showing a 7x8 grid. So this torus just kind of cut open. And light blue is a qubit in 0, dark blue is a qubit in 1. And you can see clear evidence of the expected thermal physics that you should see for an equilibrating ferromagnetic system, right? Every shot, the qubits they tend to be, predominantly in 0 or predominantly in 1, right? So we can explore both symmetry sectors of this model and see clear signatures of ferromagnetic correlations, even if we don't do any error mitigation. I think that's kind of cool, given how complex these circuits are and how many gates they have. Okay, but what we were really after is studying this intermediate temperature quench with more correlations. And here, careful analysis of what happens in MPS simulations suggests that not only at the, bond dimensions we went to do the results become unreliable, you can convince yourself that it would be pretty hard with any reasonable bond dimension that could be achieved. You might need bond dimensions, I think, beyond what's ever been run in any classical simulation to get remotely accurate answers over this entire range of time. And nevertheless, we see, pretty good evidence that the quantum data is accurate. I would say part of that evidence is just that it was accurate in the other quench, where we had a classically computed true value. I would say another piece of evidence is just that here you can see that the raw data in blue is not that far from the extrapolated data after doing zero noise extrapolation. And so the proximity of all these data points is pretty good evidence that since even if there are issues in, say, biases introduced by the noise extrapolation technique, it's not doing a whole lot anyway, because these circuits have relatively little noise in them. And therefore we can, I think, to a good degree, trust these purple answers as being accurate at late times where MPS fails badly. And once again, if you look at the raw data at the latest time, now things look a little less, ferromagnetic because we're sitting up here near the phase boundary, but you could even see, rough qualitative signs of what you'd expect, namely, domains forming on many different length scales that you should see in an equilibrated system near a phase transition. Okay, so, matrix product states are just one of many possible techniques you could use to simulate the system. The fact that matrix product state methods don't work well here does not mean that no classical methods would work. And, it's certainly impossible to prove that no classical simulation methods could work for simulating this quench. Simply because, you can't exhaustively try all the methods that maybe don't yet exist yet. And there may be many clever ideas out there. But we did try pretty hard to employ all of the best methods we knew about. So these include 2D tensor network techniques that were done in collaboration between us and Caltech. So these PEPs and PEPO lines. Things such as sparse polydynamics done in collaboration with Caltech and EPFL. And also neural network states. I'm not going to say anything about what these methods are. But I do want to give you the impression that we thought relatively carefully about what methods should work, and we tried to reach out to the people who know these methods best and work with them to develop good implementations of them for this problem. And we have not yet been able to find anything that works remotely well on the timescales that we believe the quantum data remains accurate. So in general, we see that we can capture something like, a quarter of this time range, after which all of these classical methods disagree badly with each other. And the only thing we really have to believe in out here and to check these classical methods against is the quantum data. And I think this is particularly exciting because if you imagine trying to develop these classical methods now and trying to figure out how to make them better, the quantum data that we have out at these late times, I would argue, is already extremely useful because it's the only thing you'd really have to compare any heuristic classical method to and figure out how well you're doing. Okay, so I think since I have a little bit of time left, I want to wrap up with one other simulation we did with the goal of really driving home the point that in this digital setting, we can actually see true emergence of the equilibrium physics expected in a continuous time setting. And that is through a quench in which the system is not initially in a uniform state, but it has some background energy density shown in green here. And then it has a stripe of qubits with a much higher energy density. It's kind of like a domain wall that's been inserted right in the center of the system. And this is a slightly different we're now doing a square lattice that's 4 by 14. We did that just to be able to have one more elongated direction to give us a little more runway spatially to be able to see the dynamics, the spatially inhomogeneous dynamics that results. And what we were looking for is, if you have a continuous time system that's equilibrating, you expect an inhomogeneous state to relax at late times according to the rules of hydrodynamics, which tell you in this particular case that this energy should diffuse out like a random walk. And so we can take a system like this, we can involve it in time, and I have a little movie here showing the system now, the energy density of the system diffusing out. And okay, I mean, it looks qualitatively like it's spreading out over time, although there's no, by eye, obvious sign that this is consistent with diffusion. But we can Fourier transform the spatial structure here at every time. And that's what I'm now plotting over here. This is just on the y-axis, I'm plotting a Fourier transform of the spatial structure along x of the energy density. And then as a function of time, I can plot that for many different momentum values. Every different color is a different Q value in this Fourier transform. And what diffusion tells us is that the rate at which these different Q values decay, because this is a random walk, should be proportional to the momentum squared with a proportionality constant that's called here the diffusion constant or diffusion coefficient D. And so we can take these rates computed by fitting the data and plot them in the inset here and then fit a quadratic form to it to extract what this diffusion constant is. And I think this is really neat because if you look at actually trying to do ab initio simulations of quantum materials, while we often know in some kind of coarse-grained way how they should behave or how heat should be transported in a system, what we don't know are the microscopic details, things like diffusion constants that actually enter into this hydrodynamic description. And these are things that we can now calculate accurately in a digital setting, despite the fact that they're intimately tied to time being continuous. Okay, so with that, I just have a quick outlook. I want to reiterate a point I made earlier, which is that we had to look somewhat carefully for where to run these simulations so that they would be classically hard. And the reason for that is just that 56 qubits is only a small margin outside of the limits of what one can do classically by brute force. You can simulate roughly up to, say, 40 or 50 qubits by brute force classically. And so that forced us to work in a regime of relatively high entanglement per particle, which corresponded to relatively high temperatures. And that's why the low temperature quenches we did were simulable by MPS techniques. So as we progressed on the roadmap here, our very next quantum computer will have roughly twice as many qubits and better gate errors. I'm very optimistic that this will open up a lot of space for us to go down to lower temperatures and probe arguably more interesting quantum physics in a regime that remains out of reach of classical methods. So with that, I'll just wrap up and thank the many people who contributed to this work. The people who did the bulk of the work are shown here. Reza Hagşenas really led the effort to understand how to best use tensor network methods to simulate these quenches. Eli Chertkov really led the effort to try to optimize all of these error mitigation techniques and optimize the structure of these circuits to make them run as well as possible on H2. Mike Mills was the technical lead of the H2 system while all this data was taken. But there are many more collaborators, more than I could track down pictures for. and also many external institutions that we worked with to get this done. So thanks to all of them, and then of course to many more people. Quantum is a big company, and there are a lot of people here who made crucial contributions to the design and operation of the H2 trap. And with that, I'm happy to take any questions. Thanks.